5.9. Okay, this is a bit of a curveball. It's about this Q10 temperature coefficient, which is probably the first time we've mentioned it to you. It's not terribly important what it is. I do urge you to go and check it out. There's a link in the description. You can go and you can read about what that is. Okay, it's essentially a coefficient that describes the. I'm going to read it out. The measure of the rate of change of a biological or chemical system as a consequence of increasing the temperature by 10 degrees. So an example of that would be respiration rates. What else have we got? Or it could be a reaction rate. There you go. There's some stuff on muscle performance. So it's a useful quantity, useful coefficient that describes how one thing responds to a temperature change. Okay. Now, let's go and read the question, shall we? I'm giving you the equation. I'm saying that I am measuring some rate 2, and that is equal to some initial rate 1 multiplied by this Q10 coefficient to the power T2 minus T1 over 10, okay, where R1 and R2 corresponds to the rates at temperatures T1 and T2 respectively. And in this case, I'm telling you that that relationship describes the respiration rate. That is the amount of O2 in milliliters consumed per hour by a badger. And I have made 2 measurements in the table, 2 below, one at 7 degrees and one at 26 degrees. Okay. And first, I'm asking you 2 things. Firstly, I'm asking you to work out what this Q10 value is. And secondly, I'm asking you to tell me what the respiration rate is at 13 degrees. Okay. Now, for the first part, surprise, surprise, I'm going to use logs to work it out. Let's do that. So let's rewrite that equation. R2 is equal to R1 Q10 T2 minus T1 over 10. Okay, let's take logs of both sides. Okay, we'll do it with logs, and I'll show you another. There's always some clever dick who shows me how to do it a different way every year. So I'm going to anticipate that this year, and we'll do it that way. Okay, so let's take logs, and I'm going to skip ahead. I'm going to skip a few beats here, okay, because we've done this enough now. I'm going to write log of R2 over R1 is equal to T2 minus T1 over 10 times the log of Q10. Okay, not happy with that? Send me a message on Teams, ask me. Okay, if you're able to do the rest of it, you should be able to do that. Let's just write this exclusively in terms of Q10, or the log of Q10. Log R2 over R1 times 10 over T2 minus T1. Okay. Right, so I can solve the log of Q10 initially, just by plugging in the numbers. That is equal to log of R2, which was 22.0 over 11.2, according to that table, multiplied by 10 all over 26.0 minus 7.0. I get a value for log Q10, which is equal to 0.154. Okay. Now, if this were an exam question, I would not be able to give you full marks to that answer, because I have asked you to calculate Q10, not the log of Q10. So how do you calculate Q10? Well, like this. Happy with that? You should be. Now, after doing all that, you should be happy with that. I get a value here of about 1.43. Okay. B. Find the respiration rate at a temperature 13 degrees Celsius. So this time, I've given you 2 data points. Let's draw it out here. Oh, hang on, I did promise I would try and calculate this without using logs. Okay. Let me come back to this. Let's go back here a second, and let's do R2 equals R1 Q10 to the power T2 over T1 over 10. Now, a lot of people like to do this on your calculators, which is perfectly fine. But what they do is they do R2 over R1 equals Q10 to the X, where X, of course, equals T2 minus T1 over 10. And they work that value out. And then they go, well, Q10 must be the Xth root of R2 over R1. You can do it that way too. Absolutely fine. I don't want any smug gits coming to tell me they can do it that way without using logs. I already know. Right, so. Okay, so get rid of that. Get rid of that. Come on, Rob. Right. What was I doing? Right, yeah, so I was looking at this relationship, okay? So I've given you 2 data points, like that. And it's telling you the R and the temperature. It's probably doing something like that, okay? And so, but I've only really said that this relationship is true between these 2 points, okay? Let's assume that that's true. So if I take another point somewhere here, then that's fine. But I don't know what's going on over here. So it could be doing that, or it could be doing that, or that. It's not doing that. So as long as I've got a value which is in between these 2 temperature points here, T1 and T2, then if that was R1 and then that was R2, I can work out some let's call it R3 and T3. Okay, so I'm going to ask you to calculate at a temperature. So this is, I think, 13 degrees now. So I am going to still use that relationship, but I'm going to say, I've got to be very, very careful in the order in which I put these values. So actually, maybe it's not a good idea that I call this 3 to begin with. It's going to confuse me. I would relabel this new value, this rate at 13 degrees that I'm trying to find, as R1. I call the original one T0. I call that T1, okay? So that way I can still use the same equation. So remember that R2 equals R1 Q10 T2 minus T1 all over 10, okay? This time I'm trying to find a new R1, okay? Which I know is at a temperature of 13 degrees. So solving this, R1 is equal to R2 all over Q10 T2 minus T1 all over 10. That is equal to, now I still know my R2 is, what is it? 22. Yep, 22.0. That's all over Q10. Temperature 2 is still 26 degrees minus this new temperature 13 all over 10. Right, so you can work out what R1 is in milliliters for O2 per hour. Now I haven't done it, I forgot to do it, but you can put that in your calculator and work it out. Okay, right, hope that helps.